Oh my God, somebody came. I was starting to wonder.
Oh my God, I forgot my glasses.
All right. Let me see what the font size is on this one, 18, okay. In other news, I managed to get us a replacement on the projector. Huh?
The screen?
Yeah, because it was flickering the
Yeah.
last several classes. So we got a new projector.
That's cool.
So out of curiosity, before the class actually starts, which of these two do you think you'd be able to read better? I don't know if dark is a good option or not. I actually just threw a dark theme at this and made a copy of it.
The
Just
white one.
the white
I'm
one?
kind of blind.
Okay. Yeah, if it was still flickering, I was going to switch to the dark ones because it seemed to flicker less that way. Let's see.
What if no one shows up?
Well, I got one of you online and one of you here.
Oh.
So I'm going to wait for a few because I imagine it'll be more than two, but even if it's not, I'll just power through. Hey, we're up to 3. See? But I know at the very least, out of the 4 people who tend to show up in person, one let me know she was sick the other day. Another said he wouldn't be here. And the other, who is not you, has been popping up online lately. So it's entirely possible that you might be the only person in the room. If it makes you feel better, you could sit over here or something.
Okay, that happened to somebody last night in the other class. There was just one person in here.
I saw something online. It was like a week ago. Some university teacher wanted to make the last class really nice for all his students. So he put on episodes of The Office and ordered 15 pizzas, and like 2 or 3 students showed up.
Wow.
Yeah. So, you know,
I would have felt sad.
he was trying to give away multiple pizzas to everybody that showed up, at which point I would have been like, hell yeah, but I want pizza.
3.
Yeah, right. I'll eat 3 pizzas right now. I'll do it on a dare. I don't even care. Da, da, da. 1 minute after, we have a grand total of 4 students. We're going, wait a minute. I'm shooting for, I don't know, 6. I like the idea of 6 at least. Then it's about half the class. Kind of want to go to sleep. I'm honestly not feeling great. My anxiety is spiking and I'm incredibly dizzy. So this might be a funny class. As I've said before, if I fall over or pass out or die or something, just drag me outside and pretend you didn't see anything.
Out that door.
Yeah, that'll work.
Just kidding.
I mean, that would be a little bit more painful because I believe it's a staircase right down there.
Oh.
No, it doesn't have a sign that an alarm's gonna go off. Let's poke it. Okay, there's plenty of room. There's not a class right there, is it? The hell's this door go to?
I don't know.
All right. But there's a tool chest hanging out over there, so I don't know.
Maintenance.
That took a while. All right. Yeah, I'm hoping I feel better. I'm always dying one way or another. So, something's always wrong, but when you can't walk straight, it's kind of a problem. Tried cleaning out my ears and was like, maybe that's it. Maybe it's an inner ear thing. So far, no. But we're going on 26 hours of wanting to fall over at all times. So.
Oh my goodness. We're gonna see a doctor. Probably got low iron.
Well, I haven't taken a multivitamin in like 4 or 5 months, so that might do it.
No.
Maybe I'll eat some pencil shavings or something. That'll do it. All right. Well,
Suck on a penny.
suck on a penny. Yeah. I don't know that I'm going to get any iron off of copper, although those aren't copper anyway. I think they're copper plated zinc now. It actually costs more than a penny to produce a penny.
Okay.
Yeah, we have a really, everything's just dumb.
Correct.
I feel like I should start a cult. There's now a recording of me saying this out loud.
About what?
Just a little society of people who aren't idiots.
We shouldn't have math class. We should have a podcast.
Oh my God. You don't want to get me started on philosophy. I will rant and rave for days. Okay, well, I'm doing it. We're starting. This is happening. So first up, do some homework. Nobody's doing any homework. Nobody's, okay. About a third of the class is actually using essential education, which ain't much. About a third of the class is here. So you get to wonder who's, there we go. But yeah, just listening to me talk or reading about math isn't gonna help you. Even if you don't use essential ed, it is my recommendation to at least, when you go back over these notes, write them out yourself. And don't move on to the next line before you understand what the heck you just did. That is probably the best way of actually, getting things down. I don't know where to look. I have one person in here and it's going to be really weird if I just stare at you in the eyes for 2.5 hours. That's just going to be creepy. I could look at this camera, but honestly, that's creepy to me. I hate cameras. But whatever. That's the website at the bottom to go to Essential Ed. You can't just go straight to essentialed.com because their website is funky, and depending on your login page, it's trying to log you into a whole different mess. So it has to be app.essentialed.com/start/WNC. I think there's a link to it on the Excel page. I don't really know. I don't remember. I haven't actually looked at the Excel page. I want to say in a while, but probably ever. Whatever. So for today, we're going to be reviewing the stuff that we actually did last time, which was, we started off with operations with mixed fractions. Then we did unit rates. I don't need a review slide for the word ratio because ratio means you're comparing one number to another in a fraction. Boom, there we go. There's the review for that. So we're going to review unit rates. Only have a couple of problems on there. We're going to review proportions. I got a ton of problems on there because we really only glossed at it last time. And honestly, I'm not really the cross multiplication problems that we did last time. I've never really liked them, I guess you could say. There's a couple of different ways to go about them. I showed you one way to do it, but I've never seen them as a very realistic type of problem you'll ever really see. Just being like, here, these are proportional. What's over there? Nah, we got word problems because things that are proportional usually come up in real life and you have to work on them in real life. So, that's generally where that's going. And then after that, we're going to start the next unit, which is all decimals all the time. We love decimals. So operations with mixed fractions. So as I said last time, literally just a copied over slide, mixed fractions don't work well with our usual operations because a mixed fraction is essentially its own addition problem, right? 1 2/3 is the same as 1 plus 2/3. That's the same thing. And just because of that, you can't just multiply random numbers by it because everything blows up. So whenever you're working with mixed fractions, you convert them to improper fractions. And then if it matters to, you convert it back at the end. That's all you really got to worry about with mixed fractions. So we got a couple of my favorite word problems ever. They're all on mixed fractions. This is a word problem day. And I am particularly proud of the first one. So Spider-Man ate 1 5/6 pounds of cat food last week. He is poor. He doesn't make any money superheroing. He's freelance at a newspaper. Newspapers don't care. They just buy their stuff from the Associated Press these days. What are they going to do? They're not going to help him. He lives on cat food. So this week he ate 3/4 pounds less. It might be because he can't afford more cat food. It might not. You don't know. So right now we have, he ate 1 5/6 pounds of cat food last week and 3/4 pound less this week. How much cat food did Spider-Man eat this week? Cool. So all that's really saying is that we have 1 5/6. And this week we are taking away 3/4 from that. I have no regrets on the Spider-Man problem. Okay.
And he eat cat food too.
I mean, I don't know. Maybe it was cheap. Maybe, I mean, if you're really poor, that's one of those things. Like if somebody's poor and they're hurting for money and somebody's like, yo, my cat's gonna die. Can somebody buy me a bag of cat food? I'm gonna be like, absolutely. I don't care if I'm poor. I will be more poor and eat less to keep your animals fat and happy. If they go home and eat it themselves, one, that's kind of odd, but I don't know. But whatever. Maybe he felt like cat food. Maybe there's some specific nutrients that particularly attach to a man who has a weird physiology that is embedded by a radioactive spider. I don't know. It's entirely possible that he needs cat food to be part of his diet. Whatever. Either way, this is our problem. So what we're going to do is we're gonna math it. We're gonna clean it up. We're gonna make it nice. Hey, I finally have 6 students. That's exactly how many I wanted to have. Thanks for showing up, guys. Hey, so we got 1 5/6. So we're gonna first convert this guy to an improper fraction. Remember, we do that by taking the integer 1, multiplying it by the denominator 6. So 1 times 6 is 6. And then adding it to the numerator 5. So we have 6 plus 5, that'll be 11. And that's what's up here now. Because if you tried to reduce that, if you tried to clean that up, you would be right back at the 1 5/6. Subtracting 3/4. So based on these two numbers, we need to get a common denominator. Who's got a common denominator for me? I'll be watching that chat. I don't know. We're saying 24. Now, here's a fun thing. I disagree, guys, but let's roll with it. That is a common denominator. Yes, Kelly, you are correct. It is 12. That is a common denominator. It would work, but it's not your lowest common denominator. So let's say you're working this on a test and you look at this and you say 24. It's going to happen to a lot of people, right? 2 out of 3 people just told me 24. That's a majority. A majority of people want to go with 24. So let's see what happens if we do. We're going to shoot for 24. And let me reply real quick to this message real quick. Cool. All right. So let's say 24. It makes sense. If you're working on this on your own and you're in a pinch, the first thought you might do is, can I multiply those two numbers together? The answer is yes, you always can. Can we do this with 24? The answer is, again, yes, you always can. If it's a common denominator, it doesn't necessarily have to be the common denominator, but if it's a common denominator at all, it will work. So let's shoot for that 24, shall we? Let's see what happens. So we're going to multiply this one by 4/4 and this one by 6/6. This is actually an excellent example. I like being able to do this. So this is one of those situations where I think I've mentioned it in this class before. I've tutored a lot of students who will look at their work, figure out they made a mistake like halfway through, and then just erase the whole thing. And it'll drive them crazy. They'll just erase the whole thing. And if that's what you want to do, cool. But I like to look and see if I can fix it later. Because if I can have something reducible now and I don't, I can always reduce it later. It will always work out. So we get 44/24 minus 18/24. Cool. We got a common denominator. I have actually no idea what the answer is because I didn't actually work this out. That sounds right. That sounds right. 5/6 minus 3/4. Yeah, that sounds right to me. So we would subtract these and we would end up with, I don't know, my brain isn't working. I can't even subtract today. Oh, that's not good. All right. Let's make this a fun class and how much can Ben fall apart in the course of 2.5 hours. Damn, I do want that pizza. It's in my head now. It's in my head now. So we get 26 out of 24. All right, cool. Well, what am I noticing about this? It's reducible, right? It's completely reducible. Each one of these is divisible by 2. So we can do that. 2 goes in there 13 times. That's a 3, I promise. And 2 goes into there 12 times. This thing's autofocus is freaking out. Stop trying to focus on my hand. There we go. Okay, so we get 13/12. And if we have to get this back into a mixed fraction because, oh, how much did you eat today? 13/12 of a pound. What? It's, you know, it's one of those things you could literally, if you want to see if something makes sense, say it out loud. If that just sounds dumb, it might be good to actually convert back to mixed. So you'd look at the 12 and the 13, say how many times does 12 go into 13? Once, and we'd have 1 left over, right? So we have 1 and 1/12. Now, if you're magic at this is a random thing. If you could tell that this 5/6 is already bigger than this 3/4, which it is, you could have totally ignored this 1 and just done the subtraction there, and it still would have been 1 and what we ended up with. So that's one way you could cut a corner. I love pointing out when you can cut corners, but look, we ended up over 12 because 6 goes into 12 twice and 4 goes into 12 3 times. It was a smaller common denominator. In that case, it's the lowest common denominator in that for these two numbers here. But we actually didn't get the lowest common denominator. We got a common denominator. Did it work out? Yeah, it worked out. The biggest thing you'll have to deal with if you don't get the common denominator, the lowest common denominator, is you'll have to reduce at the end. You'll just have to reduce at the end. So if you're okay with that, like I've said before, if you're in a pinch, just do it. If you see a way to do something, do it. That's fine. It works out fine. So yeah, we could have gone weird and went for 240 if we wanted to, 480, literally anything. Those would have been common denominators, just not the lowest. But if it's something we can work with, it's something we can work with. Also, since it's a word problem, I should have the units. Pounds. You could put pounds of cat food if you want. I do want to do this because it's funny to me. I literally made this problem because it's funny to me. I regret nothing. All right. So moving on, what do we got next? Here we are. Aquaman is retired to a quaint attraction in SeaWorld. He is fed 4 2/5 buckets of fish each day. The sea otters are fed 1 2/3 times as much fish as Aquaman. How many buckets of fish are the sea otters fed each day compared to Aquaman? I should actually, I should scrap the phrase compared to Aquaman, because at that point we're starting to look at technically different math. Okay. It's number 2. Let's see. He is fed 4 2/5 buckets of fish every day. I don't know how big Aquaman's stomach is. I honestly don't know if he likes seafood. Actually, I do know he likes seafood because I read an Aquaman comic and he walked into a seafood restaurant and people were horrified, and that was fun. So he definitely eats seafood. Whether or not he eats buckets of fish while living in an attraction in SeaWorld, probably not. So it says that the sea otters are fed 1 2/3 times as much fish as Aquaman. So if you're saying that, let's just say you do something twice as much. Let's say, just for comparison purposes, let's say you watched like an hour of TV one day and then the next day you watched twice as much. How would you work that out? You'd multiply, right? So even though we got weird mixed fractions, we're still going to multiply. The concept is the same. So if you don't know which operation to use in these cases, just kind of compare it to like an easier concept and think about how you'd work that out. As long as the structure is the same, you're good. Now, for this particular problem, we have 2 mixed fractions, which means we need to get improper fractions first, and then we can multiply. So let's get our improper fractions. So 4 times 5 is 20, plus 2 is 22. So we got 22 over 5, multiplied by 1 times 3 is 3, plus that 2. So we end up with a 5 over 3. Okay. And remember, this is multiplication. I don't need a common denominator. We're just going to go straight across. So 22 times 5 is 110 over 5 times 3, 15. All right. So we got 110 15ths. And again, does it make sense when you say that out loud? No, not even a little bit. Now, one thing I will do, just to make our lives easier, because trying to wrap my head around 15 going into 110 kind of hurts. I don't want to do that. That makes my brain little gooey. So what I'm noticing is I can reduce this, right? And that's because I could have reduced right here. I could have canceled these 5s and that would have made my life easier. But again, like the other one, even though I'm seeing something I could do a little easier later, it doesn't mean I can't fix it. How am I fixing it? Same way we did the last time, reduce. So 5 goes into here 22 times, and 5 goes into here 3 times. You are correct, Amanda. I like it. 22/3 pounds of fish? No, I don't like saying that either. So we're gonna get it into a mixed fraction. 3 goes into 22 7 times, right? Because that would be 21. So we'd have a 7 and we'd have 1 left over. 7 1/3. What was this in? Technically, our units is buckets. I might have said pounds at some point, but I was wrong, whatever. We were talking about buckets of fish, so there's the buckets. Way to go, Spider-Man and Aquaman. Did I just reduce both of these people to animals? I sure did. If either one of those superheroes is offended, I don't know, fight me. All right. Let's look at number 3. Ben would rate his usual level of cranky at about 5. This is about 2/3 as cranky as usual. How cranky is as usual? I should have revised this before class. It's definitely higher than a 5. I don't know. Are we going out of 10? What's the ranking? Maybe if it's out of 5, I don't know. But then again, if that's 2/3, that implies that it's higher. Whatever. Whatever. So if you're saying it's 2/3 as much of something else, just like the last problem, that's multiplication, right? So we're at a 5. And we're saying we have 2/3 of that. Or this is 2/3 of our usual. Ooh, did I break it? I think I might have broken it. Because I'm saying this is 2/3 of our usual, right? This is not a correct problem. This doesn't work because I can't multiply by 2/3 because the 2/3 is 2/3 of what? The usual. What's the usual? I don't know. That's what we got to figure out, right? So we're actually going to have to make an actual problem out of this, because if we're saying we have 2/3 of something that we don't know, it's 2/3 of something unknown. What do we use as an unknown? A variable. And we're saying right now that this 5 is that 2/3 of our usual. The word is translates to equals. It is, it equals, it's the same. We have managed to make ourselves an equation. Everything before here's a fun thing. These guys up here that we're working on, those were expressions. Why? Because there's no equal sign. We're just expressing something. Down here, it's an equation. Why is this one an equation? Because it has an equal sign. We're equating two things together. 90% of what you're going to learn in this class is literally just called whatever the heck it is you're doing with it. When you get higher in math, it's things start getting named after the weird Greek guy who came up with it. That's literally how it works. You make something else up new, cool. All right. Now, I don't think we did anything like this when we did the fractions, right? We weren't doing fractional equations. No, I have equations later in the class. So the question is, hey, how do we deal with something like this? What do I do? Well, all right. Well, let's reason through it, shall we? Let's say we have no idea what to do in an equation like this. I love freaking out people who are new to equations with fractions. It works out great every time. It's great. So if I have something multiplied onto the x and I want to get rid of it, because we're trying to figure out what that x is, right? If I have something multiplied onto that x, what do I normally do? You do the opposite, right? You divide it off. If it's multiplied, you divide. Now, I have said in the past, you don't really like thinking about dividing fractions, right? But for the sake of this particular lesson, let's just go with what we can figure out. We see this 2/3 times the x, and we're thinking, okay, we got to get rid of that somehow. So we're just going to divide off a 2/3. That's kind of ugly. Look at that. That's hideous. I don't like it. You don't like it. Nobody likes it. But what did we do when we had to divide a fraction? Well, first of all, this guy's gone. whatever we have left is just our answer, right? Whatever this thing is. Let's rewrite that for a second. We have 5 being divided by 2/3. What happens when you divide a fraction by a fraction? You leave the first one alone, which in this case is just a 5, right? But we can express that as a ratio. We learned the ratio thing last time. It's just anything that can be expressed as a fraction. We put it over a 1. But if we're dividing off this fraction, well, we flip and multiply, just like any other problem that we had to divide by a fraction. The exact same concept, exact same concept. So you multiply across. We're now at the point where you have to multiply across. So we end up with 15 halves. And the 15 halves, well, that breaks down, right? How many times does 2 go into 15? Well, it goes in 7 times out of 14, so we'd have 1 left over. 7.5. What were our units? I was just saying it was out of my usual cranky. We're going to call that a unit. We did a problem with cranky as a unit. Isn't that great? Cool. All right. I think this is the second semester in a row that I've, well, not semester, whatever. The second class in a row that I've actually used this problem, and I completely forgot to change it because I didn't necessarily want us to do this yet, but it worked out. Notice the difference in between what we would have thought we'd have to do. We would have thought we would end up just multiplying the 2 numbers together and have 5 times 2/3. What did we end up doing? We ended up multiplying 5 times 3 halves instead. We multiplied by the thing flipped upside down. Worst case scenario, that might be a shortcut that you could remember. Are you gonna? No. So every time, just do that. You're not gonna remember that. I'm not gonna remember that. I didn't remember to fix this problem. So moving right along. Cool. I've been rambling for half an hour. All right.
Flies by.
Yeah, time flies when you're talking about Spider-Man eating cat food.
Yeah.
Yeah. Maybe I'll have Spider-Man eat more cat food throughout problems in the class. The rest of the class is all going to be Spider-Man eating cat food or something. I don't know. Maybe it'll be Batman randomly hanging from a ceiling, and how long does he spend each night squeaking? That's entirely a possibility. All right. So review unit rates with our examples all on one slide, because we don't really have to worry about this one too much. It's not too bad of a concept. So a unit rate compares an amount of one thing to a single amount of another thing. We covered that last time, right? For example, the example we used last time, if a tub was filling at a rate of 10 gallons every 2 minutes, then the unit rate would be 5 gallons per 1 minute. You can just divide the numbers and make it a unit rate. So we have a couple of examples here. That I may or may not be able to just squeeze on the same page. Okay, so Lainey bought a set of 20 markers for $6. What is the cost of 1 marker? So what's the unit price basically? So we have 20 markers. At $6. Get out of my way, remote. Okay. So we got 20 markers at $6. So first of all, when you're trying to figure out which way to divide, because you could do 20 divided by 6, or you could do 6 divided by 20, which one's which, right? Think about how you want your units to be. It's going to be how much money per marker, right? So if it's money per marker, then we're going to set it up exactly like that. Money divided by marker, right? Okay. Well, how many markers we got? 20. but we need that in the denominator. So if we have 20 to $6, then we're going to have $6 being divided by that 20, right? $6 for 20 markers. Okay, so you do that division. 6 divided by 20, it would reduce to 3 out of 10, 3/10, 0.3. But we're talking about dollars, right? So we would want a dollar sign on that, and we would want to make sure that it goes out to 2 decimal places, because when's the last time somebody told you to pay $0.7? It doesn't happen, right? You'd be talking cents. Cents goes out to the second digit. So we would put another 0 there. And that's money per marker. So that's exactly how we write it. How much would one marker cost? 30 cents. Can you randomly go to the store, pop open a box of markers and say, I want to buy one? No, too bad. But whatever, welcome to math word problems. All right, let's look at the next one. If it took 7 hours to mow 4 lawns, then at that rate, how many lawns could be mowed in 35 hours? You know, if you don't need to sleep or something, but maybe you're talking about a full week or something like that. And at what rate were the lawns being mowed? Well, if we're thinking about that, what would our rate be? We're dealing with lawns and we're dealing with hours, right? So between those two, you'd normally be thinking, okay, well, our units are going to be, how many lawns can you do per hour, right? Okay. Now, if you flip this around, if you said, how many hours per lawn, that's effectively going to give you how long it takes you to do each particular lawn. So let's see, so it could probably work out either way, right? So if it takes us 7 hours to mow 4 lawns, how many could be mowed in 35 hours? Well, we can set this up. We can make this our first proportion problem. That'll work, right? We learned about proportions already. We're saying 35 hours. We could do that. That would work. That's one way to get our answer. Now, we've already done this type of math before. So we could very well just, you know, this will tell us exactly how many lawns we could do in 35 hours. Then we can find our unit amount. We could also have done it this way and worked it out for our unit amount first and multiply. Either way. So remember, if we have a proportion, we do cross multiplication. So we'd have 7x is equal to, let's see, 4 times 35, 140. And then you can divide by 7 on both sides to solve for that x, and you would get 20. And remember, x was up here, which in our proportion was a lawn amount, so that's 20 lawns. Okay, and then what unit was it shooting for? What rate were lawns being mowed? Well, that's how many lawns you do divided by however many hours you could do, right? Or it takes. So we could go back to that 4/7 and divide. Now, since we've been working mostly with, you know, fractions so far, technically you could say 4/7 is the answer. But let's punch it in our calculator. We'll get a decimal. about 0.57. And that would be in lawns per hour because we had 4 lawns done in 7 hours. And some decently big lawns, I would imagine. So which of these is our answer? Both of them. Because we both wanted the unit amount and we wanted to know how many lawns could be done in 35 hours. Now, to be fair, I didn't specify. So this isn't the only unit you could have ended up with. You could have very well ended up with hours per lawn, and that would tell you how long it takes you to work each individual lawn. That would have actually required us to do a little bit more division over here instead of setting it up as a proportion. So it works out a little nicer this way. But if you had done that, you would have had 7 hours divided by 4 lawns. You would have had basically the inverse of this guy. 1.75 hours per lawn. And you could have worked it out that way, at which point you would have been able to say, okay, well, if I'm going 35 hours and I'm trying to figure out how many lawns I can fit, I could divide the 35 by 1.75. That would have been another way to solve this problem. But what I was trying to point out from this was specifically that these are 2 completely different unit rates. And to be fair, I did not specify which one I was after. I didn't specify if I wanted to say how many hours it took to mow 1 lawn or how many lawns I can do in 1 hour. Either way, these are both unit rates, and me not specifying is totally my bad. But there's a couple of ways you can reach any of these answers. So hopefully I didn't wildly confuse everybody with that. I feel like I did anyway. Whatever. You got the idea behind unit rate, right? You divide one thing by the other thing, you get the top things units out of one of the bottom things unit, and there you go. Hey, look, we're gonna do proportions. Ignoring the fact that I totally just turned one of our examples into a proportion problem. So going back to what a proportion was, all it is 2 ratios that are equal to each other. Usually one is like bigger than the other. It's like scale models. If you have a scale model and it's, you'll have 1:10 and oh, it's 1/10 of the size of the real one. That means its proportions are all 1/10 of the size of the real one. If it's like a model car, you would say, okay, the doors are, 1/10 of the size of the other ones. All the lengths and all the widths are divided by 10. So that's what a proportion means. It's just comparing 2 things where their ratios are equal to each other. The best example I have here is the comparison of the lengths of a shadow of a small object versus the shadow of a larger object would be proportional, right? Because I mean, the sun's in the same spot and it's casting a shadow off of 2 different things, but either way, the shadow length is going to be dependent on how tall something is, right? The height of something versus the length of its shadow are going to be proportional. So usually you solve these with cross multiplication. Usually, I think I set up all of our examples to do cross multiplication, but I'm not 100%, so don't quote me on that. But let's jump right into it because I got a bunch. I got 7 of these guys. Yeah, it'll be fun.
7 slides.
Huh?
7 slides.
No, 7 problems, 2 slides.
You were like scrolling down, I was like, what?
No. The big ugly blue thing means we're looking at the next, that's the next unit. So that's when we look past, what's this unit called? Fractions, rates and ratios. when we get past that and we move into the decimals. So that'll just be doing everything we've already done with like multiplication and division and all of that, just with decimals instead of fractions. All right, so guess what our number one is? It's exactly my usual comparison. An 8-foot lamppost is casting a shadow 12 feet long. I'm gonna kind of switch over here and I'll show you how I'm doing these. So I'm gonna actually draw these kind of like triangles, kind of just to show you guys how it would work. So an 8-foot lamppost is casting a shadow 12 feet long. Okay, so that means we have something that's 8 feet tall, and its shadow is 12 feet. Okay. And we're comparing it to a nearby building that's some height, and it's casting a shadow that's 30 feet long. And you'll actually see, we're not going to worry about the other side of it, but you'll actually see that a lot of times when proportions are done, they're usually done with, say, triangles. By comparing them, they're comparing proportional triangles. Now, we don't know what the height of the building one is, right? So we just throw a variable at it. Our kind of default is X. We could have called it B for building. You could have used your first initial if you wanted to, whatever. You can call it whatever you want. You draw a small picture of an apple. I've actually used the full word monkey to show somebody that it didn't matter. I don't recommend that, but whatever. So you could see that the lengths of, you could assume that the lengths of the shadows are going to be proportional to the height of what they're working with. So if we set up proportions, what I usually like to do is write out how I want to set up my proportions. So each one I'm going to set up as height over length. And this is going to be building height versus shadow length. You get the idea. That's a B. Okay. So we can easily set that up right here, right? The height over the length. 8 feet over 12 feet. Everything's in feet. That makes our lives a little bit easier, right? Because that means our answer, this is in feet, this is in feet, this is in feet, that's going to be in feet too. I should have done one where one was in feet and one was in inches, whatever. So that ratio is going to equal the ratio for this guy. It's going to be its height versus its length. We just don't know what the height is. So we're going to have an X here, and we know its length is 30. Okay. So again, we have a problem where we can set it up as cross multiplication. So I can multiply that over there and that over there. So 30 times 8, that's 240. That's equal to 12 times X, so 12X. And again, we got something multiplied onto the variable. We want to get the variable alone. So we do the opposite operation to kind of whittle it down. If it's multiplied on, we cancel it out by dividing it off. Because 12 divided by 12, guess what, is 1. So we would have 1x left over there, right? So we know our x is, and yes, you kind of move things around. I don't have to say this equals x. I could say x equals. Works out the same. I could flip these guys around all I wanted to. So 240 divided by 12. Well, how many times does 12 go into 24? Twice. Okay, well, we got a 0 at the end. 20. And our units are feet. So it's going to be 20 feet tall. Okay. So let's look at the next one. Theo wants to use a cookie recipe that makes 36 cookies, but he wants to reduce the number of cookies to 24. If the recipe specifies using 2 cups of sugar, how much sugar should he use? Okay, so that's a proportional relationship, right? If you want to cut down a cookie recipe, you got to cut down all the ingredients by the same amount. So we're going from 36 cookies to 24 cookies. And from 36 cookies to 24 cookies. And then we're going from 2 cups of sugar to well, we don't know. That's the question, isn't it? How much sugar should he use? So we don't know. So we're going to put whatever variable we feel like. It's in cups of sugar. I'm going to use the C. Why not? Doesn't matter. So this many cups of sugar. Well, you can kind of see already that we have a decent setup for our proportion already, right? So we have, if we do cookies over cups, then we already have this thing laid out how we'd want it, right? If you do cookies over cups, it's already laid out pretty nice, right? So we have 36 cookies, goes to 2 cups of sugar. Our proportion would be, we know we're going down to 24 cookies. We don't know. Oh, did I really just say I was going to use a C and then I put an X? Yes, I did. All right. So again, cross multiply. 36 times C, guess what that is? 36C. 2 times 24, how many hours are in 2 days? 48. We got to solve for C, so just like the other problems, we're going to divide off that 36. Now, before I get this into like something neat and tidy, you can kind of see both of those are already divisible by 12, right? So I'm actually, even though I'm just dividing in this step, I'm going to go ahead and reduce this as a fraction, because basically by dividing, we've made a fraction, right? So how many times does 12 go into the top? 4 times. How many times does it go into the bottom? 3. All right. So we need 4/3. Okay, but that's not quite nice, right? I'm not going to say I need 4/3 of a cup. I'm going to actually work that out to be a mixed fraction. Usually when you're dealing with word problems, you'll give them mixed fractions. 3 would go into 4 once, with how many left over? 1/3. And that's going to be in cups of sugar. So 1 1/3 cups. Cool. These aren't too bad, yeah? They're pretty doable. All right, let's do 5 more. Hey, if nobody's going to be doing the homework thing online, you got to get your repetition somehow. You got to drive it into your skull. Let's look at number 3. In order to determine her pulse rate, June's nurse counted 18 beats in her pulse in 15 seconds. Now, at this rate, how many beats would she have to have per minute? Or would she have per minute, I should say? Okay. How many? There we go. Okay, so 18 beats in 15 seconds, how many per minute? Now you might be able, if you've ever done this sort of thing before, you might be able to just say, oh, we're just going to multiply, right? And you could. That is one way to solve this problem. If you looked at this and said, how many are in a minute, and you know you have 15 seconds and that's a quarter of a minute, you can very well say the answer is going to be this number times 4, and that's going to be in beats per minute. BPM. That's the usual way we write that, right? Now, if you don't know that, if you're looking at this and you're like, I don't know. I don't know how the hell to do that. I don't know. Okay, that's fine. Then you just do the same thing we've been doing. Make a couple rates equal to each other and cross multiply. We know we have 18 beats in 15 seconds. So this is going to be beats, and this is going to be in seconds. So we would have to set that up equal to, we don't know how many beats, so X per minute. Now, if this is in beats per second, do I want to put this in beats per minute over here? No. If this is going to be in seconds, this better be in the same type of unit. We need to make sure that our units break down nicely. We can't just have a 1 here. That's not going to work out. We can't say 1 minute because you're all going to hate me, but I'm going to do this problem twice just so I could show you what mistake that's going to make. And that's going to tie straight into me saying the other day that I had a physics professor who beat it into my skull on what it is you do your units. He actually made me do all of my problems, every single one of my problems, every single step of the way had its units written in every single step. And I'll show you what happens if we do that on this case over here. So how many seconds are in 1 minute? 60. Okay. So we would do our cross multiplication. And I'm just gonna call this 18 times 60 for a second instead of doing that multiplication, because we already know that something's going to break down to 4, right? So I'll show you what's going to happen there. If you know something is going to break down nicely, this is one way to do it. It's horribly cheap. It's an absolute corner cutter, but it works. This is 15x over here. And like every other problem, we know that we're going to divide by that 15, right? To get that x. Well, the thing is, I didn't multiply those over. So I can actually tell that this 15 is going to go into itself once, and this 60, it's going to go into itself 4 times. These cancel, and we get x is equal to the same thing that we said it would end up being in the first place, 18 times 4, right? And that's going to be in what? That's beats per. Oh, well, now that's interesting. So I'm here talking about units, and I just realized that I might be better off showing you what happens if I put that in here. This isn't wildly important for your notes. This isn't wildly important to your notes, but I want to show you what's actually happening here, because what is my unit right here? My unit's in X. My X was in what? Beats. That is specifically our answer. We got to the point of getting 72 beats. Did we get 72 beats per minute? We did not. We just know that this is how many happen in a minute. So it's kind of tricky. It's kind of tricky, but the main reason that happened is because the 15 is in seconds, the 60 is in seconds, and the seconds actually canceled out. You're not going to like doing that. You're not going to want to think about doing that. So just remember, hey, if I got beats over seconds, my X is in beats. So that's our answer right there, 72 beats. Now I want to show you, and this isn't important for your notes, but I want to show you what happens if you had actually done it this way, where you did beats per second is equal to beats per minute. Me just saying that out loud, you can kind of tell that something's wonky, right? But let's see what happens. 18, well, X over 1, we don't have to worry about that, right? X over 1 is just X, and that's in beats per minute. 18/15, that reduces down to 6/5. That's in beats per second. What we've just said that seconds are equal to minutes. That can't happen. That's a big oopsie. I'm actually gonna write oopsie on my paper here. Look at that. I wrote the word oopsie. I feel dirty. I feel dirty. These aren't the worst. Don't worry, I'll give you worst ones. It'll be fine. It's all about the core concept. I'm explaining things kind of complicated, granted. I'll give you that any time of the day. I'm explaining them complicated because I want you guys to see where things can blow up. If you're saying something is in beats per second and you're setting it equal to beats per something, it better damn well be in seconds. I mean, that's really what it boils down to. These units have to work out nicely. Now, as long as you're setting it up like this, you're fine. Every other problem that we just did, what did I do? Off to the side, I set up a ratio of how I was going to set up each one of these guys, right? Height to length, cookies to cups. My units were fine, right? What did I do over here? Over here, I did lawns per hour, right? As long as you do that, as long as this is in beats per second, you're good. You're peachy. You don't need that. You don't need that. You don't need that. You don't need that. You don't need to write any of that. You literally could have just written down this and solved. That's it. As long as you know that you have it straight for what it is you're working with, then you're good. Always. Hey, let's do more. You guys love these, so we're doing more. Didn't I just freaking do this one last time? Factory can produce 45 cars per day at 70%. How many can it produce at 100? Didn't I just do that? Well, not just. I mean, Tuesday. Am I losing my mind?
Yeah.
All right, that's fair.
Me too, though.
That's also fair. I swear I did the example on paper. Oh. I mean, I kind of did. Our example the other day was we produced 84 bicycles at 70% capacity.
Yeah, bicycle.
So that's what was throwing me off, was the 70% efficiency, because this is laid out almost exactly like our example from Tuesday.
Yeah.
So that threw me off a little bit. Whatever. So a factory could produce 45 cars at 70% efficiency. How many can it produce at 100%? Okay. How to make your life easier on these? All right. Cars divided by efficiency. As long as we have our ratios set up this way, our lives are going to be easy. All we got to do is figure out what it is we need and work it out. So the problem says we can produce 45 cars per day at 70%. And I'm gonna say on my units down here that it's in percentage efficiency, because as long as I can do that, I can get away with just having the 70 down here. The percentages aren't gonna matter because everything's gonna kind of divide off, and all we're looking for is how many cars, right? We don't know how many cars. It's unknown. We don't have a clue. But we know that we're talking about when everything's up to speed, we're at 100% efficiency, blah, blah, blah. So that's all we gotta do. That's it. So we do our cross multiplication. 40 times 100, well, it's basically 4,000. And that's equal to 70 times x, which guess what? It's 70x. And then all you gotta do is divide. Divide off to 70 on both sides. And again, I like my little shortcut. If I got zeros trailing at the end, this 0 is gonna cancel out that 0. So I can also do this as 400 divided by 7. Why do I do that? Just because I'm lazy about typing things into the calculator. So what do we got? We have 57.1429, blah, 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 blah. Who cares about 14% of a car, right? That doesn't matter. So how many completed cars can we pull off? 57 cars. And that's another useful thing to know, is when you want to round and when you don't. We're being asked how many cars a factory can produce in a day. If I say 57.14, does anyone really care about that 0.14? No, we're talking about how many cars are completed. So it would be 57 in this case. Would you be wrong if you kept those decimals? No. Technically, you are getting a fractional amount of that. So you could just kind of keep it on, but it's kind of a case-by-case basis. How many cars are you making? 57 and 14% of one. Why would you say that? Just 57 of them. You got started on another one. That's cool. I don't care. Nobody cares. Your boss definitely doesn't care. That's really it. Who's going to be asking a question like that? Your boss. Are they going to care about the 14% of a car? No. Let's look at another. Number 5. Mal's total bill at a restaurant is $34.75. Okay, that's his bill. He wants to leave a 20% tip. How much is the tip? Okay. Well, we haven't had our unit on decimals yet. That's actually a big problem I have in setting up these questions is, if I'm teaching something later and I need it for now, and it doesn't make sense to have before what I'm doing now, whole thing blows up. Really awkward to stick to a strict thing. So I was kind of in the fence of having this, because I imagine everybody here has at least seen decimals or worked with them at one point or another. So question is, what was I going to do about this? Well, I decided I was going to kind of not care and show you a cheap way of doing it. Because there's a good way of doing this. There's a nice, easy, simple multiplication way of doing this. But let's say you don't know a whole lot about percentages. You don't know a whole lot about decimals. You don't know what the heck you're doing. Let's say that you're just trying to figure it out, and you want to know how much money you're going to be out when you press that applicable button when you're paying for your money. Whatever. Well, we're going to set it up as a proportion. We can set it up as, say, the cost over percentage. That'll work, right? Because, hey, if you're paying for 3475 out of 3475, what percentage are you doing? All of it, right? You're doing all of it. So we know the percentage that this 3475 is, all of it, 100%. So if we set it up as two separate ratios, we could say, okay, well, the cost is 3475 and your percentage is what? 100. And you're trying to figure out what 20% is, right? So what's its percentage? 20. Okay, how much is that? I don't know, that's a question. Put an X there. All right. So let's say this is all we got. Let's do a cross multiplication. 100 times X, guess what that is? 100X. 20 times 3475? I don't know, grab your calculator. All right, so we got 695. Even, okay, that's kind of cool. It's also very accurate because that works out very nicely. So 3475 times 20 was 695. 100 times X is 100X. Divide both sides by 100. Here's a fun hint for something we'll be doing in the near future with decimals. What happens if I divide by 100? The decimal moves over. I end up with 6.95. This is a cost, right? So what units am I in? Just throw a $sign on there. That's how much 20% tip is on 3475. You don't even need to know anything about decimals or anything about percentages. If you know how to set up a proportion, you can figure it out exactly if you have a calculator handy, right? And that works. Now, what's the easier, oh my God, I could have just done that, why would you show me this at all sort of way of doing it? Well, you're gonna love it. 3475. That's your dollar amount, right? If you want to know what 20% of that is, you multiply it by the decimal moving over twice on the percentage. 0.2. Guess what that is? 6.95. We could have done that. That's an option. Another option. In terms of the fact that we're working proportions, this worked. If you know what you're doing with decimals and percentages, it's a little quicker. Question is, how much math do you know? Is it going to take you a while, or do you know some cheap tricks? If you don't know any cheap tricks, then hey, that's why you're here. Welcome to the class. Isn't that great? All right. It's number 6. Let's look at that one. Yeah, absolutely. Yeah, you could do it that way. If you're doing it on something that's going to be checking your work and they're asking you about proportions, you should do it as a proportion, but yeah, you can absolutely just multiply percentages. That's why I do a lot of problems with money in here, word problems with money, because suddenly if I start talking about dollars and cents, everybody knows a little bit more than they thought they did a minute ago. So it's kind of nice. All right. So Maddie is carrying a 5-liter jug of sports drink that weighs 7.5 kilograms. She wants to know how many kilograms a 2-liter jug of sports drink would weigh. She assumes the relationship between volume and weight is proportional. That's kind of important because we're kind of winging it, and it is. What is the weight of that 2-liter jug? Okay. Well, what types of units are we working with? We have a 5-liter that's weighing 7.5 kilograms. So we got liters and kilograms, right? So that's exactly how we're going to set up our problems. We're going to set it up exactly that way. If we're dealing with liters and kilograms, guess what our ratio is going to set up as? Liters and kilograms. Does it matter which one's where in this case? Not really, because when it comes to all of these proportions, if you remember when we were doing the unit rates a little while ago, the unit rates, it actually mattered which units were on top and bottom, right? That's the difference between, cost per marker and markers per dollar. But in this case, it's not really going to matter which units we put on top and which units we put on bottom, because every single one of these, we have a fraction equal to another fraction, and we just have one of these that we don't know. And whichever one we don't know is already going to have the right type of unit. So we do not care whether or not one is top or bottom. We just know that the relationship between liters and kilograms is proportional. So that's what we're working with. We don't care if we do kg over L or L over kg, whatever. So we have, initially, we have a 5-liter jug of a sports drink that weighs 7.5 kilograms. So we could set it up quite nicely that way, right? 5 over 7.5, 5 liters, 7.5 kilograms, which means over here, we're going to have liters and kilograms, right? So the question was, how much is a 2-liter going to weigh? Okay, well, we know how many liters that is. We just don't know how many kilograms. So that's where the variable goes. And that's the reason that I don't care which one's on top and which one's on bottom, because we know wherever that X is, it's going to be kilograms. If I had these all flipped upside down, the answer would end up being the same. In fact, our multiplication would end up being the same. So when we cross multiply, we're always going to end up with that 5 being multiplied by that X and the 2 being multiplied by the 7.5. That's 15. Oh, look at the division we're going to have to do on that. This one's quick. We have 5x is equal to 15. Divide off the 5. We have x is equal to 15 divided by 5, 3. What units is that x in? Kilograms. kg. That's it. That's all we need. We write that out, the world keeps on spinning. Cool. So let's look at another. Let's look at our last proportion. This is our last proportion that we're going to do. Ooh. Then I'm going to take a break and take some ibuprofen because my head's killing me. All right. So this one says Micah can eat 21 hot dogs in 66 minutes. Ugh. She wants to know how many minutes it would take her to eat 35 hot dogs if she could keep up the same pace. Ugh. Hot dogs in minutes. Is this a direct dig at my old roommate who has the same name and ate all of my food that I bought? Maybe, I don't know. I can't confirm that. Maybe that name is coincidental on this word problem. I don't know. But she hated peanut butter, and suddenly I started buying peanut butter waffles and peanut butter everything, and literally complained to my face that I was buying food that she didn't want to eat. At no point did we talk about you eating all my food. That's Ben's anger today. It's been many years and I'm still cranky. I have other reasons to be cranky. It's not just the food, but we're not gonna treat the class like my therapy session. So we got hot dogs and we got minutes. Which one's over which? Like the last problem, I'm going out of my way to say I don't care. Minutes per hot dog, hot dogs per minute, doesn't matter. We're solving for only one of those, so nobody cares. So we got 21 hot dogs in 66 minutes. That one, I'm gonna brain fart and write exactly backwards. That one means I'll have 21 over 66. So 21 hot dogs in 66 minutes. Now we're also wondering, hey, how long would it take to do 35 hot dogs? Because you just don't hate yourself enough. I hope they're at least, the Nathans or the Hebrew ones and not like, the Dollar Tree ones, because then you're just gonna die. Just gonna die. I don't know. I fully believe in using every part of the animal. So I was one of those people who went to the gas station, got one of those beef sticks. Those are delicious. I love them. Somebody once told me what they were. I was like, ugh, I could never eat that again. That lasted a week. Then I got another one. Stopped caring. It's just as tasty. If you're gonna kill something, use the whole thing. All right. Cross multiplication. Guess what 21 times x is? Hey, did I just Fonzie out loud in my class? I sure did. Didn't hit anything though. I always wanted to hit the last projector, but this one's working okay. It's not flickering. I'm cool with this. Okay, so 66 times 35 is 2,310. Which interestingly enough is the store number of the GameStop on Topsy Way that I used to live at or work at. Both words work, actually. I lived there and I worked there. Don't work at GameStop. If you ever want to get everybody fired in a GameStop, just go in, get us do their survey and say that all the employees were talking about starting a union. I learned that one real fast. You want to get fired? You'll get an entire store fired if you even mention the word union. Divide off that 21, you got 2310 divided by 21 is 110. That's in what unit? Well, it's on the bottom. Our X was on the bottom. That was in minutes. 110 minutes to eat 35 hot dogs. And let this be a lesson to all of you. If you really have to chase that dream, you might be able to do it in 110 minutes. No. I had a sausage last night for dinner. It was delicious. Did I have 21 or 35 of them? Nah. Why did I put an 8? There is no number 8. There is no number 8 at all. I am only slightly. My brain's only kind of working today. I know that seems like the norm, but okay, that is the norm. My brain's only slightly working right now because it's always only slightly working. So here we are, number 7, right before a slide that has unit 4 on it. So what we're going to do, this is a great time for our break. We're going to break until, let's see, how do we feel about these proportions? Are we 10-minute breaking or 15-minute breaking? How are we feeling? Anybody got an idea? Anybody? Oh, I got one vote for 15.
15, please.
Okay, the first person said 15. So just suddenly everybody's okay with saying that out loud. All right. Consider it done. We're going to do a break until 7:36 p.m. Pacific Standard Time. Whatever. I'm done talking. Hate it.
Yeah.
Hate it. Okay, everybody. It's been 15 minutes. You're stuck with me. I know. I'm sad about it too.
Have that long to go.
No, but I'm dizzy, so it's awkward. Fun thing is, I am going to walk home just to get my steps up for the day. I don't know where that lapse in judgment might take me, but we'll see. All right.
I just charged my Fitbit for the first time in like a month.
Yeah. I got this thing that's tracking. It can even do EKGs on this freaking smartwatch. It's cool. It's not supposed to in America, but I hacked the crap out of it. So
I want a freaking Apple one.
I don't want anything that says Apple because I like messing with them. Apple doesn't like their stuff being hacked up.
Yeah.
All right, so decimals. So the fun thing about decimal is it really means based on 10. Case in point, a lot of things in, say, computer science will be based in hexadecimal, which literally means based on 16. So, you know, you don't need to know that, but just saying there's different number systems out there, and decimal, even though when you think of decimals, you think of, you know, a point and a bunch of numbers after it. All it really means is that you're in the decimal system, and all of the numbers we always deal with are in the decimal system. So when you write numbers out, the position of each digit is important, obviously enough. You know, you got ones, you got tens, you got hundreds. But since the decimal system is based on numbers, we all know that, you know, each one of those has 10 spots. You go past 10, you go to the next digit, right? Easy enough. That works the same way when you move to the right of your decimal point. The decimal point is where things start to get below any standard integer numbers. As you move right, every position that you go is going to be 10 times smaller. You'll have tenths, you'll have hundredths, you'll have thousandths. They're always another tenth of an amount, right? So our decimal systems actually lets us write numbers as large or as small as we want using that decimal point. So digits can be placed to the left or right of a decimal point, and they show values greater than 1 or less than 1. And what we're going to be doing in this unit is really things that deal with things that go below 1. So a decimal point is the most important part of a decimal number, because without it, you're lost. You don't know where you are. It's, you know, it's like your beacon. It's your home spot. If you lose that, you're gone. You don't know where you are. So where the decimal is, that is very, very important. Hate you too, scroll wheel. All right. And on a number line, decimals tend to be, well, they're able to be appearing in the gaps between our integers. Now, this one goes between -0.5 and 1.2. So all this is here to really show you is that 0.1 is tenths. That's, you know, there's 10 of those fitting between 0 and 1. If somebody was insane enough to draw a number line that dealt with hundredths, you would have 100 points between 0 and 1. And the main thing to keep in mind here is that as things are getting further to the left, even though the numbers are getting bigger, technically the number itself is getting smaller. So 0.5 is a lot smaller than 0.1. Well, -0.5 is smaller than 0.1, I mean to say. And this is the place value chart that we did, you know, I think first class, I had this up and I said, we're only going to be working with the left part for a while. Now we're dealing with the right part. So obviously we've been dealing with the ones place, tenths, hundreds, thousands, 10,000s. Now we're dealing with tenths, hundreds, thousandths, 10,000s, 100,000s, millions. By the time you get that far over to the right, you're not even going to say that many millionths of something. You're literally just going to say 0.0111, blah, blah, blah. You're just going to say it. You're not going to have to remember what any of these are. You're just going to be able to have to wrap your head around them. So how to express or read decimal numbers. This is purely assuming you've never looked at decimals in your life. What is that 2.3? On the left side, you have a 2. The 3 is in the tenths position, so it's 3/10. So 2.3 is the same as saying 2 3/10. Likewise, on the next one, 13.76. I actually got these explanations off the internet a little bit, and I tweaked this one a little bit because I truly hated how they expressed it. Since the 7 is in the tenths and the 6 is in the hundredths, the way that I found it written was 13 and 7/10 and 6/100. But I mean, if you're going out to the hundredths point, just say it's 76 hundredths. That makes more sense. That's less annoying. Why is this here? I don't know, in case we have to say them out loud, or in case we have to translate from a word problem back to these numbers. Being able to understand how it is they're written will be able to get you to write them down on your sheet of paper and actually work it out. So all of these examples are just going to be rounding. They're going to be how we're reading them. So there's not a whole lot for me to write on a few of those. Number 2 and 3, I'll write those out on our notes, but the other ones we're really just going to say them out loud. I mean, they're easy enough to understand. So the first one says, how would you read 243.231? And obviously the implication would be I'm reading it kind of like that last slide. So you would look at the last digit and say, which place is that in? That one right there is in the tenths, hundredths, thousandth place. So I would look at this, you say the first part out loud, 243, and then you would say 231 thousandths. So that's 243 and 231 thousandths. That's really all you gotta be able to do there, is be able to identify them. Now for the next couple we can actually do some work on, right? I mean, it's gonna be quick work. We've done rounding before. But for number 2, it says round 243.231 to the nearest tenth, or to 10. And then number 3 says the same number, 243.231 to the nearest tenth. Right? Okay. So if we're doing this one to the nearest 10, that means that in your tens place, everything after it really isn't going to matter a whole lot, right? So you look for the tens place. Now 10 is not a fraction, it's going to be over here on the left, right? We have ones, tens, hundreds. So our 4 is in the tens place. So if I'm rounding that to the nearest digit here, you look at the next digit, say, okay, 3, is that above or below a 5? Well, it's below, right? So it means you round down. So this one would round to 240. Everything after that digit in the tens isn't mattering because we're rounding. Likewise, on number 3, if we're looking at the tenths, that's going to be the first place after the decimal, right? Because that's in the tenths place. So we look at that digit and we say, okay, the next digit after that, is it above or below 5? Well, it's the same digit as the last time, right? It's below, which means that this would round down. So we would be at 243.2. There we go. That's it. That's rounding. So as long as we can get a little bit of rounding here, it's good. And when it comes to problems that deal with decimals, like 9 times out of 10, every problem I've seen, 9 out of 10 problems I've seen, if I'm going to use that, I might as well use it right, tend to ask for the third decimal place. So usually you're going to round to this point where we had the 231, and anything after that's going to not matter. And you'll notice that in my examples that we do with the decimals place stuff, I usually default to that just because I've done it that way for, like 17 years or something like that. Just been doing it that way forever. The other ones are much easier, because the last one is just going to be kind of like the first one. How do you read it out loud? The first one, the first of our next couple, number 4, is saying, what is the place value of the 7 in 691.24174? All right. Well, I'm not jumping back to that chart. Anybody have an answer? What place value is that 7 hanging out in? Just remember, every time you go smaller than that decimal, every time you go, it's another 1/10 of the way to the next one, right? Anybody? Bueller? Okay. Let's look at it this way. That 2, we already know that one, right? 2's in the 10th place. You know? 2's hanging out in 10th place. The next digit, that's in the hundreds, right? The next digit, what's 10 times 100? 1,000. So the next digit, the third decimal after that, is in the thousandths place. So what would be 10 times that?
100,000.
Little off. We were just in 1,000. So what's a 1/10 of that? 10,000.
10,000.
Yeah, that's it. That's literally it. It's in the 10,000th place. That's it. You expect it to be a trick question, but it's totally not. The next one's like intentionally a trick question. I made that one up myself. That one was not found on anything online talking about decimals. I just thought that one would be fun. Why? Because I'm horrible.
Is it 10,000 or 10,000?
It's 10,000ths with a TH on that. Everything past that, since you're looking at, pieces of one, chunks of it, you're getting smaller and smaller and smaller. So it's going to be another 10ths of the way every time you go. So the next digit would actually be the 100,000ths. And after the 100,000ths, what's the next digit after 100,000? Million. So you'd be in millionths with a TH. And then 10 millionths, and then 100 millionths, and then billionths. And then, at that point, you're not really even going to say it out loud. But speaking of saying that out loud, let's look at number 5. How would I express that? What do I got on the left? Just look at the left part. What do we got? 1 0 0 0 0 0 0. You guys know what that is, right? What number is that? Chirp, 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 chirp. It's a million. That number is a million. Okay. So if that's a million, then it's a million and whatever the heck is coming out with this guy, right? So let's look at how many digits we go to the right over here. When we go to the right once, that's the 10th digit. Then 100th, 1,000th. I'm having to really enunciate the TH at the end. It's so awkward to say.
Okay.
So that's thousandths, 10,000ths, 100,000ths. What's after 100,000? A millionth. This is 1 million and 1 millionth. Why did I do that? I don't know. This is how my brain works. So it's a million and a millionth. Cool. That's all we really care about, understanding the concept of a decimal. Let's do more stuff. Let's look at comparing decimals against each other. So when learning decimal places, it's good to brush up on the greater than and less than symbols. Greater than symbol, which is, opening up towards the left, always has the larger number on the left. And the less than symbol has the larger number on the right. If you remember it that way, it's really easy to remember which one's which. The chart from the earlier class, where we covered that before, is actually here to refresh your memory. Woo! So, reviewing these, you'd have the equal sign if two values are equal to each other. You have the less than symbol when the one on the left is smaller than the one on the right. And you have the greater than symbol when the one on the left is bigger than the one on the right. Cool. That's it there. Now I'm going to have problems for this, so let's look at the problems. I'm going to write these out real quick so we can compare them and actually put our symbols down on paper. So let me write those down real quick. Okay. Oh my God, look at our problems. It's so horrible. There's all of them at once. And all we're doing is where those spaces are, we're going to do greater than, less than, or equals, right? So for number one, do we use a greater than symbol, a less than symbol, or an equal symbol? Well, if you're doing this on your own, you don't know. Compare the place values. We got the same numbers here. We got the same numbers here. We don't here. Okay, which one's bigger? On the left, right? Yeah, you okay? You doing all right? You look like you're gonna pass out. Okay.
I'm freaking blind.
Hey, I got this zoomed as far as I can go.
I know.
This is pretty big. That's gotta be like, those numbers gotta be like 4 or 5 inches taller. It's your own fault for sitting in the furthest spot in the class. Come on. Yeah, exactly. So you can line up the decimals to compare them. We got the 2s, we got 3s. On the left, we got a 9, we got a 8 on the right. So is 8 bigger than 9? No, 9 is bigger, right? Which means that the left is greater than the right. So you choose the greater than symbol. All right, okay. Same sort of thing with number 2. I set this up to be kind of a trick question. It's probably not, but I don't know. Let's ask. I know there's 5 of you sitting there. Not many of you like talking. And then there's 1 here.
Greater than.
Going with greater than? Okay. Anybody else going with greater than? Anybody going with less than? Anybody going with equals? Anybody paying attention? Anybody awake? Aha, we have 2 votes for greater than. And you would be correct. Why? Because I totally just set this up to see if you guys were looking at the decimals or the whole number overall. Because the left one has 530 and some change, the right one is 529 and some change. So you know that even though the decimal over here, 0.42 would be bigger than 0.41, but I don't care because 530 is bigger than 529, right? So that one's still greater than. But how about the next one?
Equal.
Beautiful. Both of you answered that at the same time. I like it. And for those of you who are like, what, huh, why? Because the place values are the same, 591, 591. These zeros at the end aren't going to matter. Nothing over here is going to matter because that's just 0. Who cares? All right. And then number 4. Aha, I got you on number 4. Aha. All right.
Let's.
Oh, you said less? You're saying less? What do we got? What are our votes? We got 2 votes for less? We got any votes for equal? We got any? Okay, so here's the fun part. Let's compare our place values again. 0 and tenths. Aha, yeah, there we go. In our hundredths, one has a 6 and one has a whole lot of nothing.
Oh, it's greater than.
Yeah. Because I got 2 zeros between those numbers and 1 0 over here. You got to pay attention to the place value. Yeah, 69 is a smaller number than 70, but it's the place value. If you mess that up a little bit, you might end up saying that 7 is a bigger number than 69 is. Now you'll notice that none of these answers are less than. And that's purely because the guy writing these examples wasn't actually paying attention to what the answers were. So normally you would want a nice mix of these answers, but we ended up with 3 greater thans and an equals. But hey, if you understand what a greater than is, you understand what a less than is, right? So that's, yeah, whatever. It's like how I've always said that I wanted to do sociology experiments on having a class. You guys are really lucky that I don't test you, because I have made the argument that I would absolutely love to just do a multiple choice test where all the answers are C, just to see if everybody freaks out. And then I
Please
would
do
do
that
one.
test with all
where
the answers on C, because now we're gonna know.
Well, I mean, that I would also do one where none of the answers are C, or most of them are C, except for a select few that are worth more.
That'd be a good one.
You know, or one where it says, read this exam in full at the beginning of the first page. And at the very end of the last page, it says, do not write anywhere else on the test and simply write your name at the bottom of this page. That's a possibility too. I would, yeah, you guys are lucky I don't test you, because I would absolutely just experiment on you guys all day. I'm
I'd
sorry.
absolutely fail all day.
You probably would, and that's why I would probably be fired. I mean, it's also a good thing I don't have children, because I've literally Googled whether or not it counts as child abuse to convince your kid they're growing up in the Matrix. It is, because you are deceiving them about the nature of the world, specifically because you are confusing them intentionally about the entire planet.
But we're living in a simulation.
Maybe. It depends on your definition of simulation, which also normally doesn't line up with everybody's ideas of what a simulation is. Kind of like how the scientific word for theory and the common word for theory are completely opposite. And also ignoring politics. I'm not going to get into this. I am 100% not going to get into this. Everyone in the class right now is female. I'm not going to get into this. I don't want any arguments between any of you. But the leak the other day with the Supreme Court was a leak of a draft of an opinion. And a lot of people are zooming in on that word opinion without understanding that one of the main ways that the Supreme Court actually lays down what they believe is in a paper called an opinion. The Supreme Court is literally a court that gives opinions. That is their verdict. That is their decree. So it's kind of like the word theory, the theory of evolution. It's pretty much settled. People will argue with me. It's pretty much settled. The theory of gravity, we're pretty sure on that one. It's still a theory. So, you know, you gotta watch the vocab. You gotta watch. I don't remember what the hell I was talking about. I don't. How did I get into that? I went to opinion, from theory, from where the hell did I get? I don't know. I don't care. You guys don't care.
Next thing.
On to the next thing. Adding and subtracting decimals. It's easy as pie. You guys are gonna just be peachy. Because, I mean, we've already done adding and subtracting, you know, regular numbers. You might say, but Ben, we're going to have a calculator on this stuff. Cool, I don't care. There's a section on decimals and adding and subtracting them in essential ed, and there's a section on adding them and subtracting them in the GED and the high set. I mean, yeah, you could totally just grab your calculator and get an answer, but actually having a decent fundamental understanding of what the heck it is you're doing really helps you do harder stuff. Really does. So when it comes to adding and subtract decimals, the best thing you gotta remember is literally just line them all up at the decimal point. That's it. Line up at the decimal point and subtract. So we got a bunch of these. This meme is ironic compared to what you said to me about waking up at about 4:30 in the morning. Please don't be 7, please don't be 7. 4 a.m. Sleep. Yeah. Okay. Starting off, we got 28.2 plus 93.5. You're gonna add those suckers together. Remember, you just line them up at the decimal point. 28.2 plus 93.5. And as long as you line everything up at the decimal point, guess where your decimal is in your answer? Also lined up. And then you just add like you normally would. 2 and 5, 7. 3 and 8, 11. So you put the 1 there. And because we're in the decimal system, 11 is too big for one spot. So you carry that 1. And we get 9 plus 2 is 11, plus that 1 that we carried is 12. So we get 121.7. All right, nice and easy. Let's do another. We only got 6 of these, they're gonna go quick. So we got 382.6 plus 126.5. Yeah, not bad at all, right? Not bad at all. So we line these suckers up. And add it straight down. Decimal is going to be in that same spot again. 6 and 5 is 11. So we got to carry that 1 there. 6 and 2 is 8, plus 1 is 9. 8 and 2 is 10. So we put a 0 there and carry the 1. 3 and a couple of 1s give us a 5, and we're peachy. Am I going too quick for anybody? If anybody needs me to slow down, feel free to private message me or yell at me or something. I feel like we're good. Why did I write number 2 again? Why did I write number 2 again? Only slightly disoriented. I've always told people that the back part of my brain works better than whatever part is steering. So I can do math all day, but everything I'm going to say, if it starts coming out as gibberish, just be like, Ben, you're not making any sense. Can you explain that again? Because the part's driving is gone, and the back part of the brain that knows all the math, he's on autopilot. All right, so we got 126.74 plus 82. Now 82 is an integer. So whenever you have to add to just straight up an integer, just remember where the decimal place is there. It's going to be at the end of the integer, right? So when we add that, that has to be over here. So the 1's place and the 10's place all line up. Now, you don't have to, but if it makes you feel better, if it looks nicer to you, one thing you can do when it comes to adding things like this is if they don't all go to the end, if you have different amounts of digits, you can put as many trailing zeros as you want. So 82 would be the same as 82.00 in this case. And that's just going to make our lives easier to be able to, put those guys together, because 74 and nothing is 74. Over to the left of the decimal, that's where things start getting added, right? So 6 and 2 is 8. 2 and 8 is 10 again. So carry that 1 and we get a 2. So 208.74. So in this case, the decimal places after the point don't really matter. They just kind of came with us. Yeah, it's not so bad, right, guys? I mean, you're throwing it together pretty easy in chat. I'm cool with that. Yes, I am paying attention. mostly paying attention. So number 4, we have 60.69 minus 7.8. All right, so when it comes to subtraction, you do the same thing, but there's a couple of things to remember with subtraction, just like there was before when we weren't doing decimals. It's not going to come up in this one, but remember, if you have a bigger number subtracting, or if you have a number subtracting a bigger number, then you have to kind of reverse them and then tack on a negative. That's not coming into play here, but that's just something I wanted to mention just in case it happens, because I didn't look at the rest of the problems and I don't know if I forced that to happen. I sure did. Cool. Whatever. Past Ben knows what he's doing. Present Ben doesn't. All right. So we have to line them up at the decimal, which means that 7.8 is kind of hanging out right there in the middle. Right? And like I said, you could put a 0 here if you want to. If you don't, you don't have to. If you get one of these where you have more decimals on the bottom than you do on the top, or more decimal places, I guess I should say, more place values, definitely do that. But if it's just on the bottom, then yeah, you're kind of good here. That gives me an idea on a good example. Did I say we're doing 6? We're doing 7 now. All right. I'll do a random example as the next one. So it's not too bad, right? 9 minus nothing is a whole lot of nothing coming off of that. So you're still at 9. 6 minus 8, we can't do that, so we have to borrow, but our next digit is a 0. So this one's a little bit trickier. What we're going to have to do is we're going to have to borrow to make sure that 0 has something. So we're going to chop into that 6 and make it a 5. So this is now a 10. I'm going to kind of do it that way. It's a little easier to look at. Somebody forgot her glasses. Maybe that'll be easier to look at. Yeah. Okay, there you go. Still squinting a little bit, but you know, no judgment. All right. So the next digit here, we're going to borrow that. We're going to chop that down to a 9, and then this can be a 16. So we have 16 minus 8. That's an 8. Now our next digit over here is now a 9. So we have a 9 minus 7. That's a 2. And then I got 5 minus nothing's hanging out there, so we still just have a 5. We feel good about this. We don't feel good about this. This gives me a second to make up a random problem. Cool. Feeling good. I like that. We're feeling good. Or at least one of you is feeling good. But if one of you speaks, that means you are now like a class representative. You're speaking for everyone because no one else is expressing an opinion. That's the fun part about things. Nobody else talks about anything. Only the people that talk actually have a voice. Boom. Yeah, it's right. So I made up a random example. 52.3 minus 13.002. And this one is something I'm probably just going to slap it on the equations or the problems for next time I teach this, because this is something that this is a concept that none of the other ones actually cover. And what that means is if I have 52.3 and I'm subtracting 13.002, right? That's, you know, what do you do? Because you have nothing subtracting up here from, and you're taking something away from what we perceive to be nothing. So what you end up having to do, you have to do this, is put the trailing zeros on the top one. So like I said before on the previous two, it doesn't matter if you put them there. If it's what you're subtracting, it's fine. But if I'm subtracting and I'm missing some stuff on top, you're going to want those place values to be there. And the reason for that is because now I actually have, instead of like a virtual nothing, we have an actual nothing subtracting to. So we need to borrow all the way until this can actually have something. So the first digit that has something is this 3. So we'll change that to a 2. We'll change this 0 to a 10. And then we can change that 10 to a 9 to give ourselves a 10 here. Right? It's weird to look at, but essentially what we've chopped this up to is saying we have 0.290 and 0.010, and they add up to the 0.30 that we had before. I don't know. If you're comfortable with what I'm doing on this paper, don't listen to a word I'm saying. So no, I'm going to make this overly complicated. So whatever. Decimal lines up just peachy. We got 10 minus 2, 8, 9 minus nothing, 9, 2 minus nothing, 2, 2 minus 3. Oops, so we got to borrow. That's a 4, and that's a 10. So this is now 12 minus 3, so 9. And then 4 minus 1 is 3. You are correct. You know, except for the, the comma instead of a decimal point. But I mean, again, that's a fun thing that kind of depends on the, the country. So a lot of countries actually use a comma instead of a decimal point. Bunch of them. It's legitimately surprising. The language of math, the building blocks of math are universal, but how you describe them seems to pop up differently in a lot of different cultures. Or in different ways of thinking. Do yourself a favor and never look up the term non-Euclidean geometry. On the one hand, it helped to get us an atomic bomb. On the other hand, parallel lines intersect in that type of math, and we're not playing with that. If you guys want to see something really horrifying, I helped a friend out with calculus yesterday afternoon, and I didn't expect that what I was going to do was going to take me 2 full pages on one problem. Whew, that one sucked. It wasn't even the calculus part that sucked, it was the algebra. Oh, I did have one where that kind of comes into play. Okay, whatever. So I got 147.3 minus 3.67. Same thing happens on our last example. We have to put a 0 here. Otherwise the world will blow up, or at least our comprehension of these numbers will blow up. Okay, so in order to do the subtraction, as you'd expect, we borrow, chop that into a 2, and then we have a 10 on the end. So 10 minus 7, 3, 2 minus 6, oh, got to borrow. Cross out a 7, that's kind of awkward. All right, so that'll turn into a 6, and this will now be 12. 12 minus 6, 6. 6 minus 3, 3. And then 4 and 1, subtracting 4 and 1, guess what? Those are just still there. So yeah, you're correct. 143.63. Not bad. So again, long as our decimal points line up, we're peachy. Let's do one more of these. So I have 14 minus 146.36. Good, right? So this comes into play with the fact that we're subtracting a larger number from a smaller number. And if you remember from when we covered this before, what you end up having to do is reverse them and add a negative to the answer. Because otherwise, you're not going to be able to do just straight up a 14 minus 146.36 on paper that way, at least not with our regular ways of doing these things, right? So if you're trying to find the difference between the two numbers, you usually do the bigger number minus the smaller number. And if you reverse those two numbers, everything kind of blows up. So let's not blow things up. All right. So you can add these 0.00 if you want to, or you don't have to. I'm going to do it just in case it makes you feel better and helps you understand what it is we're looking for. But again, if you're comfortable not having them or not needing them down there, you don't need them. Either way, you're going to have 6 minus nothing. Guess what? There's a 6. You're going to have a 3 minus nothing. Guess what? There's a 3. So the only thing that really comes to play are the numbers to the left, right? 6 minus 4, 2, 4 minus 1, 3, and then we have 1 minus nothing, so 1. Now, remember, this is a 14 minus 146. If you have $14 to your name and you get a $146 bill, 1, that sounds like me the other day, and 2, you're in the negatives. So that's why you have to remember to add a negative to the answer. Cool. Everybody happy? Everybody happy? We're good? We're happy? All right. Let's see what we got after that. What we got after that? After that, we have multiplying decimals, and there's 5 of those, and ooh, okay, yeah, ooh. All right. I don't think we can get through this in 10 minutes.
Maybe 1.
That's not worth it. That's not worth it. I don't want to explain the concept of something, do one problem, and then say, cool, see you guys again in almost an entire week.
Yeah.
It's not going to stick, and I wouldn't expect it to stick. So since we have reached the point where I can't reasonably explain anything else, if anybody has any questions or something that's been bothering them, random questions, I'm down for it. Otherwise, you guys are kind of done. I'm done. Like that's, yeah. So if anybody has any weird questions, throw them at me. Otherwise, yeah, I'm just gonna sit here for a minute anyway, either way. Yeah. Stop recording.